Okay, so far I have described the basic formalism underlying PCFGs, and I've described how you can learn a PCFG from a tree bank, from a set of example trees. In the last segment of this lecture, I want to talk about parsing with the PCFG. So that is the problem of taking a sentence as input. So for example, the man saw the dog with the telescope. And finding the most probable tree under the PCFG. Okay, so there is again a rather dumb kind of brute force method for doing this, which would be the following. So given this input sentence, I could somehow enumerate, brute force, all of the possible parse trees for that sentence under the PCFG. So imagine I had an algorithm that simply listed all of the possible parse trees for this input sentence. So that would be step one. In the second step, I would just calculate the probability of each of these trees. And I would choose the highest probability tree as the output from the parser. So that is a kind of brute force method where I simply enumerate all of the trees, calculate the probability for each tree, return the highest scoring tree. There is a very clear problem with this method, which is the following. The number of possible parse trees for a sentence can be extremely large, and it's actually very easy to come up with grammars where the number of possible parse trees for the sentence grows exponentially quickly with respect to the length of the sentence. So brute force search really becomes infeasible for these kind of grammars. There are simply too many parse trees to search through. However, there is a rather beautiful solution which again relies on dynamic programming. I'm going to show you how we can actually efficiently find the highest probability tree under a PCFG without having to enumerate brute force every possible tree under the grammar. And as I said, this will again use dynamic programming in the same way that we saw the dynamic programming algorithm for hidden Markov models avoided this problem with brute force search. So in the parsing algorithm I'm going to describe to you, we'll actually assume that the PCFG is in something called Chomsky normal form, which means that it has a set of restrictions on the rules in the PCFG. So a context-free grammar is in Chomsky normal form if it consists of the following. So again, we have some set of non-terminal symbols, we have some set of terminal symbols or words in the grammar, we have a distinguished start symbol. And now the rules in the grammar are restricted to take one of two forms. So firstly, we can have a rule of the form x goes to y1, y2, where x, y1, and y2 are all non-terminals. So for example, vp goes to vt, np would be a perfectly valid rule because all three of these things are non-terminals. And I have two children. I always have to have two children under this definition. Similarly, S goes to NP, VP is again a valid rule in Chomsky normal form. The second type of rule is of the form X goes to Y, where X is a non-terminal and Y is a terminal symbol. So for example, VT goes to SOR is a perfectly valid rule, or determiner goes to there, and so on. So rules of this form have a non-terminal on the left-hand side and a word on the right-hand side. So a PCFG in Chomsky normal form would have a set of rules like this with associated probabilities. Okay, so the parsing algorithm I'm going to describe will assume that our PCFG has rules of this form. Now that might at first glance seem to be a very big restriction. But it turns out that it isn't, in the sense that you can take any PCFG and convert it to an equivalent PCFG in Chomsky normal form. I don't want to go into the full details of this because it's rather laborious, but I'll just give you a sketch of the kind of tricks we can use to take a PCFG in general form and convert it to a Chomsky normal form PCFG. So let me give you one example. So let's say I have a PCFG which includes the following rule. It says VP goes to, say, VT NP prepositional phrase. Okay, so let's say for the sake of argument we have the rule. The awkward thing about this rule is that it has 3 non-terminals on the right-hand side, and so it violates this restriction on the rules. So the solution is essentially to convert this to a sequence of rules in Chomsky normal form. Let me show you how this works. So I'm actually going to introduce a new symbol in the grammar. So I'll write my first rule is VP goes to VT NP prepositional phrase 0.2. So this is a new symbol I've introduced, VT hyphen NP. And then I have a second rule which says a VT hyphen NP goes to a VT followed by an NP with probability 1. So you can see how I've basically split this rule with 3 non-terminals on the right-hand side into 2 separate rules, each of which are in Chomsky normal form. So if under the previous grammar I'd have some parse tree where I would have something like this, and I'd have some structures below these different symbols like that, in the new parse tree I essentially have this intermediate non-terminal. So the structure would look something like this. Okay, so sorry, that should be a prepositional phrase. Yep. Okay, so by doing this conversion, once I've done this conversion, I can run the parsing algorithm with the new PCFG, with the rules converted in this way, and I'll recover trees like this, and then it's straightforward to map back to the original format of the rules just by removing these intermediate non-terminals. Okay, so short story is, for a grammar which is not in Chomsky normal form, I can use various methods to convert it to a grammar in Chomsky normal form. Of course, I haven't told you how to deal with unary rules, things like VP goes to VI with probability 0.8 or something, but there are similar tricks you can use for these kind of unary rules.